As I was trying to emphasize, it turns out that secular growth is something that we encounter all the time in physics. And quantum mechanics is a place where this especially happens because we're used to using perturbation theory there all the time. And what I want to go through here is an argument why we should expect that time-dependent perturbation theory generically should be expected to fail in this secular growth kind of fashion, except for some special cases, perhaps. And so here's the argument for why this is roughly the case. So what we're doing when we're doing perturbation theory in quantum mechanics is we've got some full Hamiltonian H. H naught is some free Hamiltonian, which we know the dynamics associated with it. So if we solve some Schrodinger equation with H naught, we would know how to solve it, find all the eigenvalues, and so on and so forth. And what we do is we consider some interaction Hamiltonian, which I'm calling H int here. And we're going to assume it's got some small parameter g in front of it. And we're going to weakly perturb in this parameter g so that we're close to kind of the dynamics of H naught, but not exactly. And here we'll just assume that H int and H naught, that everything's time independent, just for simplicity. So as I think, John, you've gone over already in some past videos, we know that density matrices, rho, as we're usually used to denoting them, they evolved to according to some von Neumann equation or Louisville equation, which essentially we've got the rate of change of rho is proportional to some commutator of the full Hamiltonian with rho, and there's a minus I in front of this commutator. And this is essentially the Schrodinger equation, but for but just written in terms of a density matrix, which potentially describes mixed states as opposed to pure states, which is what a Schrodinger equation describes. So if we're going to try and solve our perturbation series here in a time-dependent fashion, what we're going to do is we need to introduce a interaction picture, or sometimes it's called a Dirac picture. And what we do here is we have to define interaction picture variables, which are basically rho of I and H int of I. These superscripts there are just meant to underline that these are different objects from rho and H int. And we're basically have to add unitary time evolution operators of the free Hamiltonian around each of these objects to define the interaction picture versions. So it's a reasonably short exercise to show that when you take the time derivative of rho of I and then use the von Neumann equation that I've earlier discussed, what you get is the von Neumann equation in the interaction picture. And so this is a bit of a cleaner equation because there's no H naught explicitly in the equation. And importantly, we've got a G out front of everything, which means that we're going to be able to perturb this much easier than the original von Neumann equation. So the idea here is we've got the rate of change of the interaction picture state is proportional to a commutator again, but with the interaction picture Hamiltonian and density matrix, and the constant proportionality is minus IG. So as I was trying to say, this is a really useful way of writing the von Neumann equation down because it's proportional to G. So what we're going to do is try and solve this in perturbation theory. So if we assume that we start with some initial state at time t equals 0, where rho I evaluated at 0, there's a way in which we can write this earlier von Neumann equation in an integral form. So this is basically, we just integrate both sides of the equation, and we've got this initial condition, rho I at 0, plus basically this same commutator, which is proportional by IG, to the original von Neumann equation, and then a time integral which goes from 0 to t integrated over S. And this is the von Neumann equation just written in an integral form. but it's going to be very useful for us to do perturbation series. So what we're going to do is basically insert this equation into itself a bunch of times. So you can see that when we take, we have an expression for rho I of t, which is, which we could just basically plug into itself. We can evaluate it at the time s and plug it into rho I of s on the right-hand side of the equation. And we could just do this forever and ever. And this is how we're going to end up with a perturbation series, which is often called the Dyson series in this context. So basically what we find when we do this is that rho I of t is basically the initial state plus something that goes like g, evaluated at the initial state. And then we've got higher order terms that go like g squared. And with every order of g that we add, we basically have to add one more integral, multiplying the initial state that we started out with. So this is kind of the general method for how do we do perturbation series for time-dependent problems. And what I'm trying to say here is, well, we should be suspicious that we might run into the secular growth problem here. So you can already see from the very first term, the term that has a single commutator with the initial state. If we could imagine just for the moment that h int of I was time independent, you could see that this scales like something that goes like t. We'd have a constant being integrated from 0 to t. So that first order term would be something like scales like gt, and so on and so forth for the higher order terms. So this is not, hi int of t is not ever actually really a constant, but this kind of just gives the flavor for why this might be an issue. It turns out that this is really genuinely a problem for a lot of quantum mechanics problems, is that we get to large enough times where t is greater than the time scale 1 over g, and our perturbation series is going to start to break down on us. So we'll be properly understanding the early time behavior for our system, but for late times, we're going to lose control over the approximations. So it turns out that there's a subset of quantum mechanics in which secular growth problems are very pertinent. And so we need a generic method to get around it. So this subset of quantum mechanics I'll focus on here, and that's the field of open quantum systems. And the idea here is that you have some really large environment or bath and some very small open system, basically. So yeah, the idea, it's in a sense very related to statistical mechanics. You've got a ton of degrees of freedom in your bath. And then, yeah, our system is typically assumed to be much, much smaller than that bath.
And when we say open, all we mean is to say is that, you know, there's interactions and sort of movement of particles and energy in between the system and the environment, right?
Exactly, that's right, yeah. And the idea is that if the system and the environment wouldn't interact, then the system would have some free Hamiltonian HS. The environment would have some Hamiltonian HE. And without interacting with each other, their Hilbert spaces don't mix. And so the free Hamiltonian describing the evolution would have this tensor product structure where HS is tensored with the identity on the environment, Hilbert space, plus the identity on the system tensored with the Hamiltonian of the environment. So, but the whole point is that we want the bath or the environment to interact with the system. And so we're going to assume that there's some small coupling G once again, and some interaction Hamiltonian, which mixes the two. So what's very fascinating about these systems is that when you're looking at what just the system is doing is basically the evolution is not unitary anymore. So in a previous video of John's, there was some discussion about how von Neumann equations essentially are equivalent to unitary time evolution of the density matrix. So this is going to cease to happen here when you're focusing on just what the system is doing. And so you have interesting effects like information can just kind of melt away into the environment. Also, dissipation can happen for the system, so energy can be lost into the environment. And basically, this is something we see in the lab all the time that basically quantum state will not stay in a perfect state that we started it out with. Basically, there's some environment it's always talking to. And open quantum systems is kind of a framework for explaining how that all happens. So what we're usually doing here is we're going to be focusing our calculations to basically compute what is the reduced density matrix of the open system doing. So what this means is if rho is the full density matrix describing the environment and the system, what that's doing as a whole, we're going to trace away the environment by an operation called a partial trace. And we're going to be left over with a density matrix, which is called the reduced density matrix of the open system, which I'll call sigma of I. And the I, again, here is just to denote that we're into the interaction picture. So the idea here is that the full Hilbert space for the system and environment has some tensor product structure. So there's some individual Hilbert space for the system, which we assume is tensored with the Hilbert space of the environment. And what this means in practice is that the density matrix for the system, sigma of I, it's some density matrix that operates only on the Hilbert space of the system after we've done this partial trace operation. And so kind of to bring this back to Earth, the kind of canonical type of problem that's studied here in open quantum systems is that of a qubit. So a two-level quantum system with two spin directions, which is coupled to some thermal bath, which has infinitely many degrees of freedom. And that's usually modeled by some bosonic quantum field. So what this means basically is that the full Hilbert space H in this type of a problem would be infinite dimensional. But once we trace away what the environment is doing, the reduced density matrix for the qubit, what the qubit's doing is just some 2x2 matrix, since the qubit has two spin directions. What we're typically assuming in these types of problems is that we've got kind of a laboratory in mind. So if we talk about a qubit coupled to a thermal bath, what we do is we kind of isolate the qubit on its own and then put it in contact with the thermal bath. And so what this would mean is that the qubit is initially starting out uncorrelated from the thermal bath or the environment. So what this means in practice is that the full state rho has a tensor product structure. It's uncorrelated. So there's some initial state for the qubit tensored with some state for whatever the thermal bath is doing. And basically what this means is that this rho, var rho of environment at the initial time, that's going to be some thermal state for what the bath is. And then finally, one other assumption we make in open quantum systems is that we assume that our interaction Hamiltonian has some tensor product structure. So there's some operator S, which acts on the system Hilbert space, tensored with some operator E, which acts on the environment. These are just assumptions that kind of simplify the math. They're not really fundamental, and people have thought of ways to get around this, but this is a very nice place to start. Now, the question is, what can we say about the evolution of this reduced density matrix for the open system, sigma of I? So if we're interested in what this reduced density matrix is doing for the open quantum system, in terms of time evolution, the natural place to start is to think about perturbation theory. Since we've got some small parameter g, we know how to do a Dyson series. So let's just simply take this earlier Dyson series that we wrote down, where we had, for the full density matrix, we saw that it was approximately equal to rho of I at the initial state. Then there was a leading order term, which went like minus IG times a commutator with the initial state, and integrated from 0 to t over the interaction Hamiltonian. And then we had some higher order things. So let's just keep it at order g for the argument at the moment. So if we want to understand what the reduced system is doing, it's actually quite simple to do this, because the right-hand side of this Dyson series only depends on the initial state. And our initial state was, if you remember, this uncorrelated state, and a partial trace is very easily dealt with for an uncorrelated state. So what we're going to do is we're just going to partial trace both sides of this equation, the Dyson series. And what we find is we get that the reduced density matrix is approximately equal to its initial state plus minus IG, and then an integral over a partial trace over the same commutator as we had in the Dyson series in the leading order. So we can manipulate this into a more pleasing form, but already at this point we can see by doing this partial trace, we've changed nothing about the secular growth problem. We can see that there's going to be definitely scenarios in which this leading order term even has some situations in which it might scale like GT once again. So this secular growth problem is not a problem that happens only with open quantum systems. However, what you find is that it's very, very often a problem in open quantum systems, probably more often than not. And the reason for this is we're very often thinking about thermal baths in these types of settings. And so one way of thinking why secular growth is a problem when studying open systems, especially when we're talking about thermal types of situations, is we should note that a late time divergence is essentially equivalent to a low energy or infrared divergence, kind of in energy space, if we can kind of think of time being related to energy. So if we've got a thermal bath, which is consisting of some bosons in some thermal state, what this means in practice is that very low energy fluctuations are relatively strong as compared to a zero temperature situation. And that's because these calculations typically depend on Bose-Einstein distributions, which are singular for low energies. So basically, a Bose-Einstein distribution is something that goes like 1 over e to the beta e minus 1. And for low energies, and remember, low energies are kind of related to these late times. So at low energies, when beta e is very, very small, this is singular, basically goes like 1 over beta e. So these Bose-Einstein factors get huge for low energies. And what this means is that correlation functions that are calculated typically, they have really strong low energy fluctuations or infrared divergences. And what you find is that this is often related to these secular late time breakdowns. And so that's one way of understanding why we should expect to see this problem for open quantum systems. So far, this has been relatively abstract, but I mentioned this model of a qubit coupled to a thermal bath. So one way of modeling this type of system is to assume that the qubit's free Hamiltonian is given by something which is basically a gap omega along the diagonals. So basically in the first component, we have omega divided by 2. And in the second component along diagonal, we have minus omega divided by 2. So there's some gap omega, and that's going to be fundamentally appearing in our solutions here. And we're going to assume that the qubit interacts with some thermal bath with an interaction Hamiltonian of the form where we've got a matrix with entries on the off diagonals, 1, 1, tensored with some bath operator phi, which is typically a bosonic field operator, which represents a thermal bath. We don't really need to get into specifics of what that all means, but the point is that that's representing some infinite dimensional Hilbert space or an operator that acts on that. And we're going to assume there's some weak coupling G. We're going to be perturbing in G essentially. So what we're going to do is once we partial trace away all the environment degrees of freedom, we're left with a reduced density matrix describing what the qubit's doing. And that's going to be just a 2 by 2 matrix. So we're going to have some components sigma 1, 1, and so on in this 2 by 2 matrix. So what we're going to do is kind of keeping with the above framework is we're going to ask the qubit and the bath to start out in some uncorrelated state. So just to be specific, we'll ask the qubit to start out in its ground state. And we're going to ask the field or the bath to start out in some thermal state at some inverse temperature beta. So I'm going to just denote that thermal state by var rho subscript beta.
Would that be the canonical ensemble, or is that a
Exactly.
microcanonical ensemble? Okay.
A canonical ensemble. So basically the free Hamiltonian, if the free Hamiltonian of the bath is HE, it's going to be something that goes like e to the minus beta HE.
Okay.
Yeah. So the quantum mechanical thermal state, basically. And so the answer here, basically the answer here that you get when you calculate what sigma 11 is as a function of time, if you do this in perturbation series, what you find is something very similar that we started out with in this video. We've got something basically that scales like g squared of t. And there's a function which basically depends on a Bose-Einstein factor, which depends on the Qubit gap and the inverse temperature. And basically in the numerator, we've got a factor of the Qubit's energy gap also. And what we see here is we've got the secular growth problem, which suffers basically this divergence at late times when t is much greater than the time scale 1 over g squared. And this is definitely not good, because what we would find if we try to calculate some probabilities with what the Qubit's doing with this is that we get infinitely large probabilities, which is definitely forbidden in quantum mechanics. So perturbation theory has led us astray here. At late times, we can't trust the solution. However, at early times, this does turn out to provide a good description.